In the second part of this series on reviewing linear algebra, we're going to dive into the interpretation of vectors and their geometry and how it relates to properties about the matrix. So you may recall that the matrix A, if it is square, it's possible that it has an inverse. It's not always true, but if it does, then there is a matrix A inverse that is also square that when multiplied by A in either order, results in the identity matrix. And the identity matrix is the matrix of all zeros except for the diagonal, which is all ones. And so it's actually a fundamental and very interesting question when the matrix A has an inverse. And so we'll get into that as we move along here. When we talk about combination of vectors, linear combination really just means that we're taking coefficients, alpha 1, alpha 2, alpha 3, and combining, adding together different vectors v1, v2, and so on. So any combination, a linear combination, just means that it's going to be of this structure. And the span of a set of vectors is if we pick all possible combinations, and that means that we just pick alpha 1, alpha 2, through alpha k to be every possible value that they could take. And so depending on how big this span is, that gives us information about the geometry. We can talk about the geometry of two vectors and whether they're orthogonal. And so this means that if we take the matrix multiplication of a row vector and a column vector, U transpose would be the row vector, V would be the column vector, and that's equal to 0, then that means that those two vectors are orthogonal. And kind of in a geometric sense, that just goes back to the idea of perpendicularity. And so this means that this would be U and this would be V, and it's the same thing as the dot product. A lot of these concepts can generalize, but for what we need, we just need typical linear algebra in kind of Rn, and so that simplifies some things. So we talk about linear independence, and this is a really important topic and concept. And so this is the idea that these V1s, V2, and so on, these are really different vectors. And so I'm saying that very loosely. What it technically means is that we can't write any of the vectors in terms of the others. And so just to show you an example, we pick these simple vectors in R3. So if we have these three vectors, these are fundamentally different because there's no way I can write one of them in terms of the others. There's no combination of adding numbers here, alpha and beta, that allow me to write this vector in terms of these others. If we take a different set instead, so if we looked at this set of vectors, even though they're all going to be different, they actually are dependent. This set is dependent because, in fact, I can write this as 1 times this plus 1 times this, and that means that because I can write this vector in terms of the others, this set is dependent on itself. And what's interesting is the rank of a matrix is dependent on how many linearly independent rows or columns it has. So if we think of A as having a certain number of columns, then if these columns are linearly independent, then that tells us the rank of this matrix. And so the number of these columns, if we can pick a set of these, say 3, that are linearly independent, then the rank is 3 of that matrix. The determinant is another related quantity. We use this to determine the rank of a matrix, in fact, or whether it is full rank or not. And so one way of interpreting, a nice geometric way of interpreting the determinant, is that we pick the matrix of the matrix A, we pick the different vectors to be the columns, or we could pick rows, but we pick the columns of that matrix. And if we allow those columns to represent vectors in that space, so if it's an R3, then we'd have 3 vectors that are pointing, and the volume of this parallel piped, this kind of cube-looking thing, tells us the value of the determinant. And one of the interesting things is if V2 if this was a linearly dependent set and I could express V2 in terms of V1 and V3, that would mean V2 lies somewhere in this plane, in the bottom plane, and so the volume you would not have this top part of this, and the volume would just be given by this plane, and that plane has volume 0. The plane obviously has area, but in terms of three-dimensional volume, it has three-dimensional volume 0. And so that's a case where the determinant of A would be equal to 0. And so when the determinant of A is equal to 0, that means that the columns are not all linearly independent. So there's some ways to calculate the determinant. For the 3 by 3 case, you pick a row. So let's just pick the first row. We pick A, and then we take the determinant of this submatrix here, which is simply just the multiplication of EJ minus IF. And then you move to the next element of that row, and we add a minus sign. So that's this minus sign. And we multiply that by the determinant of the matrix given by DH and FJ. And so then you'd get D times J minus H times F. And then when you move to C, this sign would flip again, and this would be positive here. And you would find the determinant of this submatrix, DI minus HE. And that generalizes to higher order matrices. We deal with linear systems of equations a lot when we're talking about linear algebra. And so it's interesting to reflect now that we have different tools to represent a linear system of equations in two different ways, and they have two different interpretations. So the equation y is equal to ax, where y is a vector, x is a vector, and a is a matrix, can be interpreted as the columns of A being scaled and added together with coefficients given by the vector n. And so that's shown here in this first equation, where x multiplies the first column of A, x2 multiplies the second column of A, and so on. And so we're creating a linear combination of the columns of A where the coefficients are given by x. Another way to interpret the equation y is equal to ax is to think about the vector x as a complete vector and to multiply it in matrix multiplication form with the rows of A. So R1 is the first row of A, R2 is the second row of A, and to think of this as a resulting vector where each row of A is multiplied by x. And you can think about that a little deeper to understand the geometric interpretation. So this is located or indicated with a brain slide here, and this just means that this goes into some depth that's a little bit beyond what we need for the course, and I'm just presenting it for completeness. If you like it, then that's great. You probably don't need it, so don't have to worry about all the details. The two that are worth mentioning here is the column or range space, and this is just the set of all vectors that can be found by multiplying a vector by A. So in some cases, A has some singularity in which some vectors where y is equal to ax, where some vectors y are not actually able to be written as a multiplication of a vector x. So as an example, the vector, say 1, 0, 0, there's no way to write that using this matrix. This matrix is A. There's no vector x here where I can actually get a 1 up here because all of these entries are 0. So there's actually no way to do this. And so the column space indicates which values of y are actually possible. On the other side, the null space is given by all the vectors x such that when I multiply them by A, I get 0. And so both of these together provide some very substantial information about the geometry of the matrix A. It's worth pausing and summing up some of this information for square matrices in particular. Some of this is true for rectangular matrices. Square matrices is a good test of your understanding of linear algebra. If you can explain this slide, the entirety of this slide, then you pretty much understand the gut of linear algebra. You don't need to understand every single detail for us to do well in this course, but it does contain a lot of good information here. So one of the things that we talked about is the inverse of a matrix existing. And so when that happens, if there is an inverse for a square matrix, this means its determinant is not 0. That's contrasting with the fact that over here, A is not invertible and the determinant of A is 0. We call such matrices on the left-hand side non-singular if they have an inverse, and singular if they don't have an inverse. And this also corresponds to whether the rank of the matrix is full. So if for an n by n matrix, if the rank is n, so that means that A has n linearly independent rows and columns, or not. And so in the case where it's not, the rank is less than n, and the columns and rows are linearly dependent. Oops, this should say dependent. Another interesting consequence of all of this is the fact that if A is invertible, then that means we can actually solve this linear equation exactly. And so there's a unique solution x such that AX is equal to Y. The consequences of the range space is the fact that because of this unique solution, the range space is the entire space. And that makes the null space no vector other than the 0 vector can make AX equal to 0. So this is a good summary of a lot of the key features of square matrices.